All right, so welcome to the first session for this Computational Chemistry for Experimentalists course. This is going to be a lab session where I'm going to show you how to connect remotely to the desktop computing resources and how to run Gaussian remotely using remote desktop. So I'm going to start by sharing my screen. Hopefully you can see everything. The first step is to download, I'm going to do this all on a Mac, by the way, but how to do it on PC should be pretty straightforward. So the first thing, anytime you want to connect remotely to any TCU resources at all, you have to start by downloading this F5 Big IP Edge client. I've done that already. You connect to the TCU VPN, which requires your password. And I have two-factor authentication turned on, so I need to use a separate code that's sent to my phone as well. Once that's done, open a browser and go to a web page that shows me all of the tools, rather all of the remote desktops available for me to connect to a TCU. This is https labaccess.tcu.edu. / and / confused, but I can still get there. Let's see. If I use the right slashes. So we see there's a whole bunch of things available. I believe you can only connect to this web page after you've done your VPN connection. So I know that the Gaussian and Gauss viewer installed on this GIGA lab. So I'm going to connect to one of the Windows computers there. Now what I get when I click on connect is on a Mac, I download a thing, and that thing is a file that gets opened by Microsoft Remote Desktop. Double click on that, that opens Microsoft Remote Desktop. Here's a key thing. I have to type that I am a TCU /user. Otherwise, it'll just look for my name on that computer and say, there's no account BGNESCO on this specific computer, so goodbye. Now I type in my password, and I should be able to connect. Blah, 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 certificate cannot be verified. We'll just pretend we didn't see that. Click through some stuff, and now this is the desktop of a computer at the TCU library. And that computer at the TCU library should have Gaussian and Gauss View installed on it so that I can use those to run my calculations. Now, a billion different app defaults have to be reset, so I'm just going to turn off the remote audio because I don't need to hear an alarm for that every 4 seconds. Now, the next step is to find the Gauss View viewer. So I'm going to go to search, Gauss View. I get a warning. I ignore that warning about .ini file. I get a second warning, and this is something that we have to attend to. Will not be able to execute Gaussian using the following command line because the defaults for the old version of Gaussian don't match the new version of Gaussian that we have. So that's going to be the first thing we need to change on these lab computers. Now, ideally, this is a part that you should only have to do once. So we click through that, we get a splash screen, we get a second splash screen. I don't want to see tips at startup, so I'm going to close that. And now this is the thing you have to do once. Just as an aside, it may be that some of this stuff gets fixed later. One of the ways you can test that Click there in your new molecule. Now I have a new molecule, and I go up to the Gauss view calculate to see, can I run a calculation? Can I submit a calculation? No, that's grayed out. I need to tell Gauss view where is the Gaussian 16 executable that I'm going to use. For that, I go to File, Preferences, Gaussian Setup, Job Setup. Now here I'm going to execute using a custom command line. So this first variable is what version of Gaussian do I use? Run the job, input file, output file. So what I want to do is C, I'm going to use a custom command line and change this to be C G16W G16W.exe. Now I think I have that right. So, okay. Now this is just telling Gauss view where I can find Gaussian. These are things that hopefully will be fixed before you have to do this, but if not, you may need to do this once every time you log on to a new desktop. So that's set. I'm going to close Gauss view. And now I'm going to reopen it so it sees that new setting. Failure to locate .ini file. I can ignore that warning. I didn't get the second warning, which means things should work. So now I'm going to do a calculation of the molecular orbitals of methane. This window is a new molecule. This window is the thing that I'm going to build. So I could add fluorine atoms, I could add phosphorus, I could use different hybridization of carbon, but I'm just going to add CH4. Now I can move this around by shift click. I can zoom in with control click, and I can rotate it with just click and drag. Now, the next step is calculate Gaussian calculation setup. So I'm going to use the default calculation type, Hartree-Fock theory, 321G basis set. You don't need to know what any of that is. The job type is going to be the energy. We're going to do all of this, explain all of this later on in the course. For now, just use the defaults. It's molecular orbital theory. It's freshman chemistry. Now we're going to submit the job. The first thing we have to do is save an input file. It will probably make your life easier if you save in each session, you save all of your input and output files in your documents folder on the local machine. Then every time you're done, or every time you've done something you think you want to save, you move those files out of the document folder on the local machine. You move them to whatever shared drive you want to use. If you don't do that, they'll be lost, they'll be destroyed, they'll be gone. You'll have wasted your time. I'm going to call this CH4 because it's going to be a calculation on methane. All of these other defaults I'm going to leave, and I'm going to save it. Now I'm going to submit that file to Gaussian. This is the Gaussian 16. It's running the calculation. It ran very quickly. Now it's done. And it's going to ask me, there's two files that I could open, a checkpoint file and a log file. The log file is a text file that tells me some information about the molecule. The checkpoint file is a binary file that saves the coefficients of all of the molecular orbitals. I want to look at the molecular orbitals, so eventually I want to open that checkpoint file. For now, I'm going to open the log file. It opens in a new window. I'm going to close the old window. Now I want to look at the molecular orbitals. To do this, I need two more steps. And the way things are set up right now, to do those two steps, I need to run them from the command line. So this step, you're going to get an introduction to using a command line in Windows. Once we get to any scientific computing, the working on the cluster, you'll be using the command line almost exclusively. But we're going to show how to do it on Windows. The new, latest and greatest version of command line in Windows is a thing called PowerShell. So I'm going to search for PowerSh, get Windows PowerShell. It sets me in some random default directory, so I'm going to change directory, cd, c, \, users, I can type in USE and tab, and it will autocomplete to users, BJA, and autocomplete BJNESCO, DOCU, tab, and documents. Then I hit enter, and I'm in that directory. I do dir to list what's in the directory, dir enter, and I see my ch4.chk, ch4.gjf, ch4.log. Those are the files that I've generated in Galaxy. The first step is to convert this checkpoint file that's a binary file into a text file that's human readable. To do that, I'm going to use a utility called formchk, format checkpoint file. Once Gauss View is set up, ideally, all of this stuff is sort of done under the hood and you don't have to worry about it. It just sort of does some of these things automatically. But we're not going to do them automatically today. I'm going to show you the details. So we're going to go to the we're going to execute form check to generate a formatted checkpoint file. So I happen to know the location of that is c:\G16W. I tab and I see that I've got the right directory, formch, hit tab, formcheck.exe, put a space, type in the input checkpoint file that I want, that is my initial binary file, and then ch4.fchk is going to be the name of the output file that I want. So I tell form check, here's my input file, here's my output file, hit enter. Now I hit dir and I have a new formatted checkpoint file. I could open that in Notepad and I could see a bunch of, let me look at it actually. I'll go to my File Explorer, go to my documents, and I'm going to open this with blah, 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 blah. I don't want Dreamweaver. I don't want any of that nonsense. I want just Notepad because it's a text file. It's stuff about the method that I use, the number of atoms, the Cartesian coordinates, the x, y, and z coordinates of all the atoms, and I scale down, and I scale down, and I have a bunch of numbers that are the molecular orbital coefficients. You will almost never look at these files as text files because it's very difficult to extract any information out of them. What we're going to do is we're going to visualize the molecular orbitals. And we're going to do that using another Gaussian utility called CubeGen. So this generates a cube of points, an XYZ cube, and at each point it gives you the value of one of the molecular orbitals. And then you can visualize that. So I'm going to go back in PowerShell, we're going to go to CG16W CubeGen.exe. And now I have to type in the arguments for CubeGen. First, how many processors do I want to use? 1. Second, what thing do I want to calculate? MO equals 5. The 5th molecular orbital. Methane has 10 electrons. It has 5 electron pairs, so there's going to be 5 occupied orbitals. So this is going to be the highest occupied orbital. Next, I put in where do I want to get the molecular orbital coefficients from. That has to be a formatted checkpoint file. I'm going to use ch4.fchk. Next is where do I want to put the results. So I'm going to call the ch4-homo.cube. And now I have to tell it a little bit of extra information about what I want that cube file to look like, how many points to use and stuff like that. So you just put 0 space, little h space. Now hit enter. CubeGen generates that. Now I use the up arrow to say I want to run almost the same command, but make a new file called ch4-lumo.cube that is molecular orbital number 6. Hit enter again. Okay, now I've generated those cube files and I can use Gauss View to look at them. So I go up here to the results tab. Sorry. I'm going to close the log file. I'm going to open my formatted checkpoint file. I'm going to results, surfaces and contours. I'm going to load a cube file, ch4 homo.cube. Let me bring this picture up. Now, that's a cube filled with points. So I'm just going to generate a surface. So I can't look at every value of points and values in three-dimensional space. What I'm going to do is I'm going to plot the surface of all points where the molecular orbital equals plus or minus some cutoff value. Zoom out by control-click. So there's the highest occupied molecular orbital. The HOMO and HOMO minus 1 are degenerate, which is why the molecular orbital doesn't have the same symmetry as the molecule. There's a degenerate orbital with opposite symmetry. So now I'm going to hide that surface. I'm going to show you what happens if I choose a larger threshold for my new surface, this ISO value. So now rather than plotting all the points where the molecular orbital is plus or minus 0.2, I'm going to plot all the points where the molecular orbital is plus or minus 0.04. That's a smaller, more compact looking picture. I show the old one, hide the old one. Show the old one, hide the old one. Now I'm going to hide this one, and I'm going to look at the lowest unoccupied orbital. So I'm going to load the cube of CH4 LUMO that I generated before. Highlight, make sure that the LUMO is highlighted, do a new surface, and there's the lowest unoccupied orbital. It has more S-type character rather than P-type character. So it's sort of a combination of the sigma antibonding orbitals from the 4 different CH bonds. Those are the things you need for the first lab. So that should be all you need. The last thing that you're going to do, now I'm not going to do this to show you because I don't know where you want to save your files, but the last thing that you want to do once you've finished your project, close Gauss View, open your File Explorer, you go to your documents and you take all the files that you generated today and you move them someplace where you can save them. You can use Box, you can use another directory, whatever you want, but you move them someplace where you're going to save them. I'm not going to save mine, so I'm just going to delete them. And that's it. Now I can sign out of my remote desktop session. Stop sharing my screen. And that should be all that you need.